Hey class, this is Professor Nick Sensky at UNC Charlotte, and this is the continuation of the Week 3 tutorials, which are dealing with data structures and recursion. And a common algorithm that combines these ideas is the fractal. And fractal is a self-similar sort of like geometry. Basically, pieces of the geometry are going to repeat and recurse pieces of the core geometry. So let's actually try to take a look at what that looks like here. This is an algorithm for something called a Koch Snowflake, or like a Koch. It's K-O-C-H. I'm not sure how to pronounce that, but basically like the Koch Snowflake is kind of like a classic fractal. So I have a script here. I'm going to go ahead and run that for you. It'll just take a second here to crunch. Okay, so this is a Koch Snowflake, and make sure to get the editor up here. So basically, the algorithm is that there is basically like a triangle that then gets replaced with a shape that looks like this. Okay, and then those shapes get replaced with a shape like this, and it basically like recurses. So it's just going to become, if I like zoom in, I can sort of see this like star shape. If I zoom out, the whole thing kind of has that star shape. So that's kind of the idea. I'm going to go turn off the grid here. That's kind of the idea of a fractal. So what I'm going to do today is I'm going to go through a series of fractal algorithms for you. Basically, I'm going to show you some diagrams that correspond with the code, so you understand how the like fractal logic works, as a means of understanding how you could design your own fractals. I'm going to go through two classic ones and one sort of like generic fractal algorithm, and hopefully, again, this will give you some ideas about how to manage data structures and how to do recursion in your designs. Okay, so the first one, let's go ahead and take a look at this Koch Snowflake. This is from the MIT Department of Architecture's written tutorial called Hello 3D World. From their one of their RhinoScript scripting classes from a few years ago. This particular script is written by Josh Dorkson, excuse me, and I've modified it to Python from its original RhinoScript. But again, this is a pretty common like algorithm. This is Josh's implementation of it, but this you'll find in all kinds of like computer science textbooks. Okay, so right off the bat, we're going to import RhinoScript. And import math, and we'll see why we need math like right away. We're going to define a breakpoint. As you guys know from earlier, it's very important in loops that you have a termination clause. In this case, we're going to be using basically we're going to be using a loop, and we need to know when to stop that loop. Otherwise, it's going to go on into infinity. And in terms of like recursion or whatever, it's going to infinitely like recurse until the length of one of these segments becomes smaller than this number, and that's how we know that we are going to stop. Okay, if this number gets bigger, we'll have fewer like iterations. If it gets smaller, we'll have more iterations. But it's very important to have a termination clause in your loop. We'll take a look at that later. Okay, actually, I'm going to go ahead and show you guys a diagram that I've created for this, so we kind of understand how this works here. Okay, so the first part of the code here is actually going to draw the points of a triangle. So we draw a point at 0, 0, 0, and we draw a point at 3, 0. And basically, this is creating the base of the base of the base triangle of the core triangle. And then the third point is the one that requires a little bit of math. We have to actually use the like Pythagorean theorem, as it says, which is the square of the base and the square of the height is equal to the square of the hypotenuse. If we don't know what the height is, we can subtract the square of the base from the square of the height, and if we take the square root of that, we will get the height of this. So in order to construct this kind of triangle, that's basically what we're doing up here with this math. So we use math. Square root 9 is 3 times itself, and then we use math power. So we take 1.5 raised to the power of 2. That's what that means. and we get height, which is the location of this coordinate, and that ends up being something like 2.598 if I round it, and we know that it's halfway between 0 and 3. It's 1.5, and so that actually gives us the 3 points of the triangle. So these are point 1, point 2, and point 3. Okay, then we go ahead and we define that by drawing lines, and we end up with like line 1, line 2, line 3. Okay. Then we have a function called draw triangle. Okay. And we're actually going to skip this for now because I want to look at this other function here called split line, because draw triangle actually calls split line. And this is a pretty common structure in the design of an algorithm. Like you have sort of like a utility that you write as a function because you know that you're going to be calling it pretty frequently. And then that way, in your main algorithm, you can just call it as a simple function. So we've separated that from the function, and we're calling it split line. So let's take a look first at what split line does. So this is split line. Okay. If we look at, we have a line, just any kind of like generic line, and we look for the line domain. And what the domain basically is it tells us where the where the start and the end of that curve are. It basically is a list, and the 0 index of that list is the first point of that line, and the 1 index of that list in this case is the max of the line. Okay. Curve domain will change depending upon the number of points you have in the line, but in this case, since it's a simple line, it's just a segment actually. That's going to work for us really well. And then what we do is we subtract max from min, which is going to give us the length of that line, like the location of that line. And then if we divide that by 3, we get the location of 1/3, like along that line. So basically, like the domain is essentially like a way of understanding parametrically and in a normalized way how long this line is. So it makes it very useful. We don't have to exactly know the math of it. We just have to know where we are along like the domain of that line. And then in order to get 2/3, we subtract max from min. We take that times 2/3, and that gives us the location of like 2/3. So these are essentially these are all 4. They're points along a particular segment. And what's cool about this is it's going to work no matter what angle the line's at, what like rotation it is, whatever length it is. It's going to automatically help us do that. Then we're going to trim that line, and the first line we're going to trim. Now we call this line. The first line we're going to trim is we're going to go from the min to 1/3, and we're going to trim it, but we're not going to delete the line. That's where this false light comes in. And then we're going to do the next line is going to be from min plus 2/3, right? So here, and then max, and then it's going to go ahead and give us this part of the line, and we will delete that. And then we get a list called split line that contains start line and end line. So start line will be at index 0, end line will be at index 1, and we return split line. So what we get when we put a line in is we get a list with the 2 segments of that line at index 0 and index 1. Okay, that's what that does. Let's go back now to draw a triangle and see how that works. Okay, so take a look at this here. So we make an array to store the lines. We're just going to put 2 empty things in there for angle. Then we're going to split the line, and that will give us these 2 lines, right? Then we're going to reconnect the 2 lines with a line that we're going to call angle 0. We're going to put it in the put it in the array at index 0. So that's a line from the endpoint of this first one, right, to the start point of the other one, of the other line split. And that's what we're going to draw. So it's going to draw this line here. Then we're going to rotate that 60 degrees. Right? So we take rotate object, the object is called angle, we're going to rotate it at the curve point, split 60 degrees. Okay, so that tells us the point and the angle we get. And then we're going to connect it with the other split line. So taking that, we're going to add a line from the end point of this piece to the start point of the other piece. And that will end up with 4 lines. So split 0, angle 1, split 0. That's our piece. Now what is that going to, and then we basically say, we have a point in the loop here where we say, if the length of the curve, angle 1, that's this, is less than our smallest curve, we're going to get out of the loop. We're going to stop looping. Okay. Otherwise, we're going to recurse. So now we're going to call draw triangle, this whole function again, on split 0, angle 1, split 0. So this is the recursion. We have a function here, draw triangle, and we're actually calling that function within itself. So this is where the recursion is happening. You have a function that can call upon itself. And so what that's going to be is that the line in draw triangle is going to be split 0 and 1 and 0 and 1. And what that looks like is this. So we're going to split all those lines, and then we're going to add the pieces to those lines, and so on and so forth. And then these will be split, and then they'll be added. And that's the how the Koch Snowflake works. Okay. Again, you can change the amount of recursion by changing the breakpoint in the loop. This piece of code down here basically just automatically runs the script as soon as you start the program. So we say like main is kind of the main like function that's like running in like RhinoPython, and we're just saying like if that main function's running, which it is when we click play, go ahead and start running this program. So we're gonna draw a triangle with line 1, line 2, line 3. So we run the program, it's gonna draw this, and then when we get down here, it's gonna go ahead and run. It's going to go ahead and run this recursion. So if we go back again to a new piece again, we'll see what it looks like. So you can see it kind of draw. It starts down here. It's going to recurse through here. But then it'll go ahead and recurse through all these. And that's the Koch Snowflake. Okay, so so that's a pretty common algorithm. Okay, the next one that I want to talk about is the Sierpinski Triangle. Actually, I don't. Got it right here. All right, so let's take a look at what a Sierpinski Triangle looks like. Again, pretty common algorithm. This version of the script is written by Ken Field Griffith, currently a PhD student at the MIT Department of Architecture, also part of Hello World, Hello 3D World. Again, I've adapted it to RhinoPython from its original Rhino script implementation. Once again, we have a breakpoint that's defined by the smallest curve. This is very similar in structure to the other one, but actually like quite a bit simpler. Let's go ahead and run it quickly, just so we can see what it does. And I'm actually there we go. Yeah. And it's going to recurse and then stop here. So it's actually a little bit different than the other one. So whereas the other one was kind of doing a subtractive operation and then adding lines, this one is actually more like additive. Like it's just adding it's inscribing some geometry within some other geometry. And again, you can see how there's like some self-similarity within this form, right? That there's a triangle with a triangle inscribed in it, with a triangle inscribed in it, and so on and so forth. And this becomes like very like self-similar all the way through. So this is a Sierpinski triangle, okay? And how does that work? Take a look at another set of diagrams here. Okay, so first off, this is basically instead of using some math as a function, it's actually drawing it with explicit coordinates. This is a decision that they decided. You can see, so there's a point at 0, a point at 2, and then there's basically, once again, creating an equilateral triangle with points. Then we're going to add lines to those, so we have line 1, line 2, line 3. Okay. Then we have the function Sierpinski Triangle, and Sierpinski Triangle, like again, is recursive. It's going to call itself here, but this is actually much simpler. All this one is going to do is it's going to say if the curve length of one of the segments on the triangle is smaller, stop the loop. So once again, we have our like termination clause. That's where it's going to stop. Otherwise, we're going to make 3 triangles, and the way we do that is, kind of not convoluted, but a lot of explicit code here. So we're going to if we put a triangle in to a Sierpinski triangle. it's actually a list of 3 lines. Okay, so when we do that, we change the data structure of it. So now line 1, line 2, and line 3 become triangle 0, triangle 1, triangle 2. Okay, and then what we would begin to do is we start to draw lines explicitly within there. So the starting point of triangle 0, the midpoint of triangle 0, the midpoint of triangle 2 to the starting point of triangle 0, and so on and so forth. So we draw these three triangles, and then what we end up with now is numbering them like this. So 1, 2, 3, 4, 5, 6, 7, 8, 9 counterclockwise. It's a pretty common convention in 3D geometry is that we draw shapes counterclockwise. We make surfaces counterclockwise. So just kind of bear that in mind. Then we call Sierpinski Triangle on those collections, and so now this becomes a triangle, that becomes a triangle, that becomes a triangle, and these will run concurrently until they all hit their breakpoint. And that's what you see when you run it. And then once again, we just run the function at the bottom again. So Sierpinski Triangle is pretty... So we start to inscribe triangles, and then we'll inscribe triangles, and so on and so forth. So once again, let's just take a look at Sierpinski Triangle. There we go. So again, you can kind of play with that breakpoint here. Be very careful of that because it's really easy to kind of crash Rhino if it takes too long to draw. But again, it's infinitely self-similar. It just exhibits a lot of the kind of properties of a fractal algorithm. Okay. So there's that, and then the last one I have for you is a generic fractal, which is adapted from the book Algorithmic Architecture by Koch Snowflake, teaches at Harvard University. This is on page 88 to 93. This is actually written in Metal Script, which is Maya embedded language, and I have adapted it to Rhino Python. Okay, the way this algorithm works is that you have some kind of a base shape that the fractal is going to be applied to, and then you have what's called a generator, which is the sort of the fractal shape that's going to be applied to the shape. You might call this the kind of seed, and this is the generator. But anyway, so the only requirement is that this shape, in order for it to work best, has to have a starting point and an ending point that are on the same x coordinate. Okay. Otherwise, the results get kind of weird. Not that that couldn't be something that you could experiment with, but I'm just saying it's going to give you some unexpected results here. But this is a good kind of thing to play with to get you some kind of non-standard fractals. It's a really nice general algorithm, and I like it for that reason. So let me go ahead and run it for you. So if I run the program, it's going to ask me to click to save to choose a generator, and I do that, and then it's going to kind of pause for a minute, and then it'll draw that. So you can see the self-similarity here. It's pretty nice. So it's kind of this object, inside of itself, kind of like it ends up becoming kind of like a cross, which is kind of cool. And it's recursing, several times, and you get these nice kind of overlaps and things. So that's a nice, kind of non-standard, what I might call like a non-standard fractal. But again, you could do it with anything. So if I was to just draw a simple kind of shape here, it's going to do that. So depending upon the shape that you have as the core, you're going to get a different kind of negative space with this. So that can be really interesting. Let's go ahead and take a look at the diagram of that and how that script works here. All right, so right away, there's 3 functions in this fractal, and basically the core function is called fractal, but it makes use of 2 other functions: get vectors from points and fit. Okay, those are the ones that are actually doing a lot of the heavy lifting inside of fractal. So let's actually go ahead and start off by taking a look at a fit. Okay, because that's actually the one that needs the most explanation. So fit starts off, you have a start and an end and a shape, and basically what happens is that you give it 2 points that are the start and the end of some segment, and part of fractal actually is what's going to give that to us, and then shape is basically your generator shape as a list of vectors. Okay, but in this case, they're basically points in this case. But having them as vectors allows us to do some mathematical operations on them. So you're going to get the first point or vector in the array, and that's a point here. That's going to be PT. Okay. Then you're going to draw a copy of that shape, basically. Okay. And that's just pretty simple. You're just going to go ahead and you're going to say like add curve. It's going to add all the points. It's going to be like a 1 degree curve, which makes it straight lined. So you have a thing called new curve. Okay. Then we're going to go in and we're going to scale that curve. And we go ahead right away. We figure out, first of all, what the length of this line is from start to end. That's what temp n is going to be. So the vector length of that is mag. Then we're going to find out what the length of this is by taking the array. So we go the length of the array shape minus 1. So whatever the last point is in the shape minus the first point in the shape gives us a temporary point. We find the length of that. So we have mag and amag. And the scale factor is just basically a ratio of this length divided by that length, which is just going to tell us if we multiply this by some scale factor, how is it going to fit that? Okay, and that's basically what we do. So in this case, in this kind of illustration here, I figure out what the length of the first piece is up here, and I know I have the length of this and the length of that, and I go ahead and I scale it. I say scale object new curve starting at point by the scale factor in all 3 axes, and that gives me this, which is longer than this. It could be smaller too, but in this case it's larger. And then I'm going to rotate it into alignment, and to do that I figure out what the angle is. Basically, it's not exactly this way, but I figure out what the angle is between the start point and the end point and the base plane, basically. And that gives me, if I do a tangent squared, like an arctangent, I'm going to get the angle x. Then I'm going to rotate that object starting at point, the number of degrees. It's very important to convert that to degrees because it actually comes out of this in radians, at least in Rhino. We're gonna rotate that, and now you can see already that this is actually going to match up with that now. So that's the point. Then we move it just like I just did, actually. Basically taking it from, I subtract the vectors from this point here, the 3 XYZ vectors. Actually, sorry. So start 0 minus 0.0, start 1 minus 0.1, start 2 minus 0.2. So just the XYZ vectors minus these XYZ vectors will actually give us the vector to move it from this point to that point. And in fact, that's what I do. There's a utility function in here, vectors from points, and all it does is it just simply, it makes a vector array, it gets the points from that, and it just transposes the XYZ coordinates to be the XYZ vectors of a new vector. And then it just basically keeps adding each vector to a list of vectors, and then it returns that list. So it's basically just a translation. Sort of like a utility function. And again, we use that vector math in different places here to sort of make some of these operations simpler. Okay, and okay, let's get into fractal. So if we look at the fractal algorithm, it's actually pretty simple. Let's just take a look at this. So the generator is the when you click and to choose the object, that object goes into fractal. We take that object, we call it generator. We find all the points on that object, put that in the generator. So it's a list of all the points in our generator object. Then we make an array for the base objects, just an empty array. Then we make a list of all the objects of type 4, which is curves and lines, and we remove the generator object from that list. So what we want is only a list of the things that are not the generator. That's a way to do that. Then we have a loop here for I in the length of the list. So for all the objects that we have, if we have 1 object or 2 objects or 100 objects, right, we're going to iterate through that list. we're going to take the first object in that list, or basically like whatever like I is, like wherever we are within this list, and we're going to call it base name. And then we're going to change all of the points in that shape to vectors, and we're going to call that new list of vectors base. Okay. Then we're going to erase that object. So we would actually erase this. We're gonna translate this into a list of points, then into a list of vectors, and then we're going to delete it. Then we're going to call the fit function for every point within that shape, and we're going to go ahead and basically start. Actually, I'm sorry, I shouldn't say. It doesn't just delete the one segment. It actually deletes the entire. It's going to delete the entire object because we have all the points in memory. Then it's going to iterate through those. So it's going to say basically first point to the next point, send that segment into fit, and generator, which is our list of vectors which represent a shape, is going to go into that fit function. And then that fit function is going to run, and we're going to get this. Then it's going to go to the next set of points in a base. So this point to its next point, and it's going to run it again. And then it's going to go to the next one, and so forth until we run out of points in the array. Okay, and it's just going to iterate through that. And the recursive part is actually going to come in. This is a little bit differently recursive. It's not recursive in the sense that the function gets called upon itself, but rather the fact that the function gets called time and again, and it just keeps performing the same operation. So whereas the first iteration of this is going to just perform an operation on these 4 segments of this object, of this shape, the second iteration will actually be calling it on 16. Okay, and then the next one is going to be so basically it's just going to keep getting called on more and more objects, and because it's self-similar, that's where the recursion comes from. So it's going to essentially be a square of it each time. The way that we actually run the Fractal program is where that recursion comes from. So first of all, we get the object, so that's going to be my gen object. We're going to use a while loop in this case, and so what I've done is I've set a counter. So I've got 0 is I. I'm going to say 5 iterations. So that's the number of times that we're going to run the Fractal. And I'm going to do a little trick here. So I'm going to, because it gets very slow. If it had to draw everything in front of us, it'd be very slow. So I'm going to disable the redraw, but basically saying enable redraw false. Then I'm going to recurse. So I just keep basically running Fractal on all the objects in the scene here, and then once I run Fractal, I'm going to add one to that counter, and that will send us back through the loop again, and we'll do it basically we're going to do it 4 times because it starts at 0 and we want to be less than 5. And then when I'm done with that, I call redraw again, and it's going to draw what's in the buffer. So the lesson here is basically to extract this idea of what a generic structure for a fractal looks like, so that we can experiment with recursion, and we can write our own custom versions of fractals. And basically, it looks like this. I mean, you have either some kind of like replacement rule, like a substitution in this case, or as in with the Koch Snowflake, you have a sort of like a transformation rule where you apply some kind of transformation which turns it into a shape. Or like the Sierpinski Triangle, you're simply basically taking a shape as a structure to draw another copy of that shape in sort of like a recursive inscribed way. Okay, so whether it's additive or transformative or a substitution, the basic idea is that you've got some kind of like recursion going on. So something that like iterates, that actually calls itself, and at some point you're stopping the loop because you don't want the recursion to go on forever. That might be because you've got some clause that says if it gets very small or it gets very big, stop, or only run it for X number of iterations. Okay. And it's very important because, again, you could create an infinite loop and you'll lock up your computer and you won't even be able to get the shape out in the first place. But it's a very, very generic sense. Like, this is how fractals work. So anyway, hopefully this was helpful. The scripts are going to be posted online. I will try to get a link to them in this YouTube channel to a site that's accessible off campus. If you have any questions, let me know. Thanks.